lecture of magnetic effect of current. Here we shall discuss about the magnetic field generated due to a current carrying solenoid, and we shall apply the Amperes law to obtain the expression of magnetic field inside the solenoid, and we shall also see how the lines of force of the magnetic field produced by a solenoid looks like. So first of all, a solenoid is an insulated copper wire packed closely in the form of a helix, which is shown in the figure. And by long solenoid, we define that the solenoid is very large as compared to its diameter. It is large compared to its diameter. This is called the long solenoid, and here we have shown the enlarged view of this section here in this picture. Enlarged view of a portion of a solenoid is shown in the figure, and these lines with arrow are showing the lines of force, magnetic lines of force and field due to a solenoid. The field inside a solenoid is uniform. Here cross marks here and the dot marks here. The cross marks denotes the point where the current enters the plane of the paper here, and the dot marks denotes the point where the current comes out of the paper. It is a wires are coming out here and they are wounded in this fashion here, and they are coming out through this line and they are going into the plane through this line. And as they are coming out, by applying the right hand thumb rule here, the wire is coming out of this point marked by the dot. We can see that the rest of the fingers are curling around this direction. So these are the direction of the magnetic lines of force due to each individual wire coming out of the plane of the paper, and they are going into the plane of paper here, and by applying the thumb rule here we obtain the direction of the magnetic lines of force. So here we can see that the lines of force cancels each other here, but they are adding up in the axial direction. Along this direction they are adding up, but along the vertical direction they are cancelling each other. Look here and here they are same. The resultant vector field, the resultant total magnetic field of the solenoid is the total vector sum of the field due to each individual turn, and the field due to the neighboring turn add up along the axis of the solenoid. Look here, for this where this turn it is along this direction, this along this direction, so they are adding up, and they cancel along the perpendicular direction, which I have just seen here. They are cancelling each other. So by combining this effect, we get this kind of lines of force, and the field inside the solenoid, which we can see here, is uniform in nature. And how to determine the polarity of the end of a solenoid? It is called the Amperes rule of polarity. Suppose we have a solenoid here, it is shown, and now if we hold the solenoid with our right hand, keep in mind it is our right hand, if our fingers point along the direction of the current, these fingers are pointing along the direction of the current, then the extended thumb, this thumb, will indicate the face of the solenoid having north polarity. Here it is shown. This is the north polarity is shown here, and this is a standard rule for obtaining the polarity of any end of the solenoid. So we can see that this is our solenoid. If we apply the Amperes rule, we can obtain the polarity of the solenoid. Next, we are going to obtain the magnetic field due to a long solenoid that we have already discussed. We have that long solenoid means its diameter is negligible compared to its length. And now similarly here the cross mark denotes the point where the current enters the plane of the paper, and the dotted line denotes the point where the current coming out of the plane of the paper. Here sectional view of a long solenoid is shown. Here these are the dotted lines denoting the current coming out, and this cross mark denoting the current entering. And here the lines of force are parallel, meaning that the magnetic field is uniform inside the solenoid, and it is zero outside. Look here, it is zero in the vertical direction. outside it, the solenoid, the magnetic field is 0. So if we apply the Amperes circuital law, we have line integral of B dot dl is mu 0 I. So we have an Amperian loop ABCD we have taken, ABCD a closed loop. For the integration purpose, we apply the Amperes circuital law. So we can just write B dot dl as from A to B, B dot dl plus B to C, B dot dl plus C to D integration B dot dl plus G to A integration of B dot dl. So we have the closed loop B dot dl can be written as the summation of this 4 integration from A to B, from B to C, from C to D to D to A. This completes the closed part. And suppose the length of this segment is CD is L. Now let us see again. So if we consider first the integration from the point B to C, B dot dl. Here we can see that the magnetic field is directed along this direction and the length dl is along this direction. So the angle between them is 90 degree. As we know, B dl, B dot dl is B dl cos 90 degree, it is 0. S cos 90 is 0. Similarly, along this direction, it is D to A. It should be D to A, B dot dl. Here similarly, the angle between L and B is 90 degree. So we again have B dl cos 90 is equal to 0. So these two portions cancels. So we only again have from here C to D, B dot dl. Although it is the angle between B and dl is not 0, but as we have already discussed, the magnetic field outside the solenoid is 0. As they cancels out outside, so B is 0 outside, so this integration also 0. So we only have the portion A to B. So closed loop integration B to dl, B dot dl gives us from A to B, B dot dl. Again here the angle between B and dl is 0. So we have A to B, B dot dl is equal to B dl cos 0. So B dl, and if we take the distance between D to C or A to B is L, we have B dot dl is equal to BL. And if we suppose total n number of turns per unit length of the solenoid, small n is the number of turns per unit length of the solenoid, then there must be total, if we have n number of turn per unit length, then this in L length we shall have NL number of turns. And if we consider I current is flowing through each of the component, each of the turn, then total current is flowing, I will be equal to, if I is flowing through each turn, then total number of turn is NL, then NL and I. NL through I will be the total current. So B dot dl according to Ampere's law is equal to mu 0 I, that is NI into L. As we have obtained B dot dl is equal to BL, so BL is equal to mu 0 NIL, LL cancels out, so we have B is equal to mu 0 NI. So the value of the magnetic field due to a long solenoid is equal to mu 0 NI, where N is the number of turns per unit length of the solenoid, I is the current flowing through each turn, and mu 0 is the permeability of free space. So by applying the Amperes circuital law, we can obtain the value of magnetic field due to a solenoid.